Technically, I feel as though I should have just
Okay, everyone. Put those distractions away.
Get those distractions. Howdy, dude.
Okay. All right, so there's kind of two sections of notes. We have a little bit from last time we need to finish, and then there's the section about catalysts we skipped that we need to go back and talk about as well. So the first thing is last time we talked about graphing and how you can graph things to determine the rate law for the reaction. Someone remind us, if something is a first order reaction, which graph gives us that information? Good. Natural log versus time would be linear for a first order reaction. Now what's cool is first order reactions also have another pattern with graphs to them, and it's specific to first order. So with what we're going to learn about right now, keep in mind that this is only for first order reactions. But first order reactions have what is known as a constant half-life. So when you do look at the graph of concentration versus time, they will always have this beautiful exponential curve that perfectly is incremented. Now, if you've taken chemistry before, you may have learned about half-lives when you talk about radioactive decay. We don't really talk about it in AP in that sense because nuclear chemistry just isn't part of the AP curriculum. But the idea of a half-life is if I have a sample, okay, let's say, so for example, when you get, has anyone ever had a bone scan before? It's not an x-ray, it's different. I have, but just curious if anyone else has. So with a bone scan, what they do for a bone scan is if something doesn't show up on an x-ray, a bone scan's another method to look at the bone in a different way. So what they literally do is they inject you with a radioactive isotope that latches to the calcium in the bone, and then when they scan it, it lights up in their thing, and so they can see the bone even closer. Like I had a fracture that wasn't showing in an x-ray, so they did a bone scan to check it. But with a radioactive isotope, they have half-lives. And so over time, they decay, and so it's no longer in my body. It's not like I'm still radioactive, right? So for example, I think iodine, the one they used, had like a half-life of like 4 hours. So what that means, if they inject me with, let's just pick 10 milligrams, in 4 hours, I'm only gonna have 5 milligrams left. In 4 more hours, I would have 2.5, because it always is cutting in half.
What if it?
But never gets to zero. Oh, good point. It is changing into something else, but the thing it converts into is not a radioactive substance.
So that
Eventually.
So that substance is still in your body.
Possibly. I don't know what it decays into. Yeah, possibly. But it decays into something that's not like dangerous. Yeah. Yeah, great point though, Ethan.
Can something? Can it like half and half and half so that it's all gone, or is there just a little bit left?
Yeah, so great point. So normally with an exponential graph, like mathematically speaking, do exponential curves ever reach zero?
No.
No. But chemically speaking, can they reach zero?
Sure.
It is dry.
Yeah, because eventually you're going to get down to a single atom, and you can't turn it into a 0.5 of an atom, right? Like mathematically speaking, you can cut numbers indefinitely, but actual matter, so eventually it does reach zero, right? Now, in terms of atoms, sometimes that can mean like a really long time. So all radioactive samples have a half-life, but we can also use half-lives just to describe a normal reaction and how it proceeds, and that's what first orders do. First order reactions have this constant change over time as the reaction proceeds. So it's just another way where if you're given a graph with half-life and the half-life stays constant, it's another way of being like, oh, I keep claiming that's a first order reaction because only first order reactions do that. And we also have an equation, so put this in that little box right there. This equation's on your formula sheets, you don't need to memorize it. So T of 1/2 is the symbol for half-life. So we can find the half-life of substance by taking 0.693 over K. Once again, this is on your formula sheet. You don't need to know it, but the significance of point, you're like, what's the point of 693? Is this actually equals the natural log of 2, which is what links it to this idea of cutting in half. But what this is really cool, is once I have a K value, which we learn how to find in a variety of ways, I can then plug K into this equation to know, oh, what is the half-life? Once again, recognize this equation only works if it's first order. Because if something's second order, the T of 1/2 isn't a thing, it changes over time. So here's an example. I'll be honest, this equation in terms of you using it on the AP test, like, shows up every few years. So it's like,
is it time for our rotation?
I don't know.
Wait,
I mean, you never know, because they could, I wasn't on last year, so maybe. But you never know what they'll do. The biggest thing is if you read a question about find the half-life, just remember you have an equation for it, it's really simple. Most of the time where students get stuck is they're like, how do I find half-life? And they start like trying all these random math things. When you can just plug it in there. So, but here's an example, this was a few years ago, but here's an example of an FRQ question, not finding half-life, but related to half-life.
So we're allowed to use our sheets on the AP test, right?
Yes, yes, so you'll get your formula sheet, you'll get a periodic table, so don't memorize them, we just wanna get comfortable with them, so. So this problem says that the reaction is first order. Explain how the data in the table is consistent with it being a first order reaction.
Okay.
Okay, so we already know it's first order, they're telling us that, but how does this data support it being a first order reaction? Now, a common incorrect way students have gone with this question is they start doing what we did at the beginning of the unit and looking at like, oh look, well, this doubled and this didn't change, and they start doing that process, which is a good process, but not with this data. Does anyone know why that process would not work with this chart?
First of all, it would be zero order.
Say that again, Sam.
Like we already know it's the first order, and it's for the first order graph.
True, so we do already know, but you could use it to justify your claim still. But that is part of it as well. Other thoughts? This chart is missing something very important when you do the comparison. Grant?
The rate.
The rate. You have to know the rate to know how it's being affected. None of these values, T of 1/2 is not rate. Temperature, volume, pressure, like those are not rates. You need the rate in order to do that comparison, which we'll do on the lab, so we'll get practice with that as well. So the catch here is I know it's first order, and it's really simple once you know the answer, but this question trips students up a lot, is the justification is that the half-life stays constant, and first order reactions are the only things that do that. Now it did change under what circumstance?
The temperature, no, yes, the
Yep.
temperature being the reaction.
So when temperature changed, then the half-life did change. Why would that be? Good, so we know in general that temperature makes reactions go faster. Good. What else in relation to like the equation of T of 1/2? Eden?
Because molecules are moving faster, where they're moving faster, meaning there'll be less of them, like, fast.
Yeah, and so they'll keep hitting and making it all go faster.
Oh, sorry, because temperature is also K, so in the reaction, it's a larger divisor, so the O may get smaller.
Good. Yeah, little k, our rate constant, is dependent upon temperature. It's constant if temperature doesn't change, but if temperature changes, k will change, and if k changes, then this is gonna change because of that equation, right? But what would be different is like if this was a second order reaction, it wouldn't be constant half-life. The half-lives would change when you start changing other factors as well. So, yeah, Sophia.
How would you find K in this?
You wouldn't be able to from this.
Okay.
Yeah, great question. Yeah, we do not have enough data to find the actual value of K. So,
Can you just like, you like take the half-life and put it over the natural log 2 and then find K from that?
oh yeah, that's true. We could find it actually because we do have T of 1/2. Good job, Aiden. Has my do that. So yeah, technically, if you have this, you can find K. Is of algebra, right? So we can plug in 100 and then rearrange for K. But in terms of our normal way of like writing a rate law with K, we don't have that kind of data on this problem.
What was the number for the half-life occasion? What was the number you wrote on top of the K?
0.693. And that's the way it's written on your
Is it
formula
like a
sheet.
is it like a constant?
Yes,
You
it
use
is.
always?
The natural log of 2 equals that
Oh,
number,
okay.
so it
That
never
makes sense.
changes. I wrote it both ways because I think your book wrote it as natural log of 2 over k, but it equals that number. So yeah, great point though, Aiden, that number never
Wait,
changes.
it's
So
natural log?
the natural log of 2.
I always thought it was natural law, and I was like, what law are we talking
Oh,
about?
the natural log, because it's connected to like log base 10, mathematically speaking, we're not gonna go there, but, so. Any other questions on that so far? Okay, flip your notes back to, I don't know where it is, but the section about catalyst.
Oh, yeah.
If someone finds it, tell everyone else what page it's 11.
I took the AP quiz on this one, like,
Oh,
the
Oh,
assigned quiz.
dang it, you missed that memo. Don't take it.
Yeah.
Oh, wait.
Got like 2 out of 6.
See,
It's fine though, I got like 3 out of 5 on it.
see you here.
I'm gonna write that down.
All right, did everyone find that section?
Yes.
Okay.
Yes.
So catalyst, we talked about them briefly. We're gonna get into a little bit more detail, but honestly not a ton. You could like spend months about talking about the ways catalysts work. 1 month. Just a month. I'm a little out of it. I got my COVID booster and my flu shot yesterday.
In both arms? Why would you do that? Just like plug it in on both arms, just like
I
we
guess
got
the
this.
pharmacist said that's what they like to do, so that if you have a reaction, they can tell what caused it. But I was like, both my arms. This one's way more sort of the balance, so it's okay. The one I gotta write it. But if I'm a little out of it, that's why. Just a shot. Get a shot before. Yeah, I don't feel
When I
it.
got my COVID shot,
I'll be fine by tomorrow.
literally was like,
But I do feel a little like, that's why I keep putting my sweater on and off because I like it cold.
I was just like everywhere except like super normal. Just like felt like a patient.
Yeah, it hasn't been, it wasn't as bad as my first dose of vaccine.
Yeah.
But like last night, I like felt pretty sick. But
My first one I didn't
not at all. That's weird, huh? Yeah, because some people just like. Okay, so with the catalyst here, everybody, a catalyst is something we add to a reaction like we've talked about with mechanisms, right? We put it in, and then it comes back out. Now, how they work, that's where we could spend months on, okay, is
I sprayed my toe.
they work in a lot of different ways, so we're just going to focus on kind of just the overall categories of how they work. Biggest takeaway number, once again, is that they provide the reaction path with a lower activation energy. That's how they make it go faster. Now what that means is it could end up, so the red line represents a catalyzed reaction. It may result now in 1, 2, 3, 4 steps to get to the end, but because the overall energy is lower, it actually still goes faster with the catalyst. So sometimes it makes it look more complicated in the mechanism spectrum, but in terms of overall time, it goes faster. So let's do for a smiley face, don't say it out loud, but circle in this mechanism. You can talk to your table buddy, but circle the catalyst in this mechanism. Don't say it out loud, but circle the catalyst.
I actually do know kind of how to observe this.
See, no, I already knew that. Like, how do I find a rate law?
Yes.
Oh yeah, no,
Hey,
that's
from
the
rate
rate
law. How do I find a rate law depending on slow and fast?
Oh, it is.
Wait, mechanisms was this unit originally,
Yeah.
right?
In
Yeah.
and out of fast.
Weird.
And then intermediate is something that gets created.
Which is I.
Yep. IO would be an intermediate.
Okay, if you circled I minus, have a smiley face because that is the correct catalyst for a reaction.
I can't believe I haven't used a single smiley face yet.
I haven't either. but I
Now-
have so many.
I know, same. So good.
The way the pathway works, everybody, that's where it can get quite complicated. So I'm going to give you an example of a few different types of catalysts and how they kind of create a better pathway. Key thing to remember is collision theory states that in order for a collision to be successful, you have to have proper orientation, and enough energy. So a catalyst is going to influence one of those two things to help it go faster. One example of a catalyst are catalysts that bind to a reactant to help it react in a certain way, and then they release it at the end. This is an example of how enzymes in our bodies work. If you've taken biology, hopefully familiar to you. Right, so enzymes bond to the substance. Most of the time with enzymes in our body, they're helping break down food. And so it helps break it down, but then the enzyme releases the product and can be used again. One example that some of you may experience in your own life is if you're lactose intolerant.
Oh, I am.
It's
Yeah,
because your
it's
body doesn't have the enzyme lactase.
It's just because I'm Asian.
Is there really a trend?
Yeah, that's the thing.
Yeah.
It's
Oh,
because
really?
like when
Most Asian people.
when Americas were colonized and
Where is
stuff,
that?
you know.
Like you don't go to China and be like, hey, can I get some milk? They're like, what?
Asia just never was.
Yeah, because
Yeah.
But, like,
so did, like, a bunch of
Everybody drinks
countries.
goat milks and that doesn't have like.
Right. It's
in Europe there was a mutation that caused it so that people past a certain age were able to consume milk still, because before that mutation everyone was lactose
And so it's
intolerant at a
normal
certain
to
age
be lactose
because
intolerant. Like the people that aren't lactose intolerant have the mutated gene.
Yeah.
yeah, because
Like,
we're pretty much
population is
I didn't know that.
drinking like milk.
Yo, let's
It's
go.
like for babies we drink milk.
It's
We're
like
basically just drinking another animal's milk.
Right.
So
It's unlactose.
Yeah, no, that makes sense. But I didn't realize I never the connection to like
that's true though.
So, anyways, everybody. So with this idea of a catalyst, right?
No, ice cream.
Give me your attention here, everybody. So when someone is lactose intolerant, it's because they don't have that enzyme in their body to break it down. What's really cool now is with science and how they've discovered things, they've actually synthesized the enzyme lactase. So if you are lactose intolerant, you can take a pill before you eat something like ice cream, and your body can digest it better because you now have that enzyme. What's interesting is I never thought of is it doesn't stay like a natural enzyme that's created, which I don't quite know why, because it is still a catalyst. You know, so I'm partially lactose intolerant, like not a lot, but like certain things. And so, but like I have to take a pill every time.
Well, I think it's
Because maybe it's something different, yeah. Yeah, I'd have to look, I've never thought about looking at the structure of like synthetic
Maybe-
versus like the natural one.
maybe the reason it's like that is because in certain environments enzymes go out of commission. and,
That's right, they like
use. So maybe it's like a one-time use.
Yes, something about how that was structured.
Something,
Yeah,
yeah.
you can't drink straight milk. Or else bad things happen.
Another type, everybody.
And cheese, I love cheese.
Yeah, really your understanding of catalyst just needs to be they speed up a reaction by lowering the activation energy, and then they can work in a variety of pathways. Yeah. Okay, here's just a few other examples of the way catalyst works. So you do have covalent bonded catalyst, where in this, so this is a very long mechanism, that's what this crazy picture showing. But what I want you to circle here is the H+. So the H+ starts here, it binds on, then the reaction goes, all these things happen, and then at the end, it got released. And so it was a catalyst in helping the reaction take place. And in organic chemistry, you'll learn how that works more so. But Aiden, do you have a question?
It's more of an idea.
Yeah.
Did you ever get a cup of milk and put the pill in it and just wait till it dissolves and see what happens?
No, I did not.
Interesting.
Maybe if you drink it, it won't, like the lactose is gone.
Yeah, I don't know. But like watching it break it down and just see if it does anything.
It would just become like water.
That's a cool idea, Aiden. I don't like have any lactate pills on hand, but oh, it is the weekend.
If it doesn't explode, then we can do it just like right here.
Yeah.
Yeah, keep us updated.
All right, I'll go check Walmart and. Great.
But it would turn the lactose into
Theoretically, yeah. Yeah, we'll talk a lot more about it when we do acids. So, another type of catalyst is a surface catalyst. Once again, notice there's all this trend of it latches, the reaction happens, and then it releases. So surface catalyst, right, some sort of surface that just increases those chances of successful collisions happening. It's just another example of a type of catalyst that exists in the world. So, any other general questions about what catalysts are, how they work? Two big takeaways for AP chemistry are: one, a catalyst is there in the beginning, it's there in the end, and in terms of a graph, it lowers that activation energy. Recognize it's not going to change like the start and end, but it provides a pathway that requires less energy to get there. So, okay, I'm going to pass out your lab, that is our review/pre-lab, and then, actually, let's do this first.
I thought this was.
That was last time's lab.
So let's do next period, right?
So that is, yes, so that's your one homework assignment, is the graphene lab from last time is due next time. Yes, our battery made it, right? Oh. Hopefully it didn't stop during that notification.